Okay, I put some class notes on Lewis structures and covalent compounds. I'm going to do another video on just Lewis structures if you need help with that. So for now, we're going to start super simple and just do the Lewis structures of individual elements. All right, so let's say I want to draw the Lewis structure for something like, I don't know, strontium. Well, strontium has 38 electrons, so drawing the Bohr model would take a lot of work. That'd be a lot of circles. But if I draw the Lewis structure, all I have to do is draw the valence electrons. So I'm not sure if you guys remember, but if you wanted to figure out valence electrons, it's based off of the group. Yes, there are groups 1 all the way through 18, but remember that I don't really like that system. It's the newer system. I like the old system. It's called the AB system. So all of these tall columns here, those are your A groups, and then all of your transition metals, those are the B groups. So this is 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. I like that better. I think it makes more sense because the group number tells you how many valence electrons. So everything in group 1 has 1 valence electron. Everything in group 2 has 2 valence electrons. Group 3, 3 valence electrons. 4 valence electrons, 5 valence electrons, all the way to the noble gases with 8 valence electrons. So let's go back to strontium. So if I wanted to draw the Lewis structure, all you have to do is, so strontium, you're going to put the symbol in the middle, and then you're going to say how many valence electrons it has. Well, strontium has 2. So 1, 2. 2 valence electrons. That is the Lewis structure for strontium. Easy. Now we can also draw the Lewis structure for the ion that would result from strontium. So strontium is a metal. Metals are going to lose their valence electrons. How many valence electrons does strontium have to lose? 1, 2. So it's going to lose 2 electrons. And when strontium loses 2 electrons, it becomes strontium. It lost, so now it's positive, and it lost 2, so it's positive 2. This is the Lewis structure for strontium positive 2. So it looks just like the regular formula that we always do, but for nonmetals it'll look a little different. So it has no valence electrons, so I didn't draw any. Let's say I wanted to do a Lewis structure for a nonmetal. Let's pick something that has a ton of electrons. Let's try tellurium. Actually, that's a semi-metal. I'm gonna go with selenium. Selenium has 34 electrons. That's a lot. So let's try and draw the Lewis structure so we can see how many valence. Well, selenium is in group 16, but we know that this is actually 3, 4, 5, 6. This is actually group 6A. So because selenium is in group 6, it's going to have 6 valence electrons. So to draw the Lewis structure, you write the symbol. Selenium is Se, and then you put the valence electrons. 1, 2, 3, 4, 5, 6. Notice that I put 1 in each little quarter before I started pairing up, because electrons are negative, they don't really want to be next to each other. So there's 6. Well, selenium only has 6, but every atom wants to reach that perfect octet. It wants 8. It's easier to gain 2 than to lose 6. So, and also selenium is a nonmetal. We know nonmetals gain. So he's going to gain 2 electrons. When selenium gains those 2 electrons, he now has a negative charge. Because he gained 2, he is negative 2. And then, of course, if he gained electrons, he no longer has the 6, he now has 8. 1, 2, 3, 4, 5, 6, 7, 8. But in order to show that all of these electrons belong to selenium, we put brackets. And then the charge goes on the outside of the brackets. So for nonmetals, it looks a little bit different. You must have all of the valence electrons with the brackets and the charge when we're doing the Lewis structure of a nonmetal. For the metals, you don't have to have any valence electrons because metals give up theirs when they become ions. So there's no brackets because you don't have any electrons to account for. All right, let's take this one step further. So we had our individual Lewis structures for strontium and selenium, and then we showed their ionic Lewis structures. Well, now let's see what happens when these two come together and form an ionic compound. So here I have my metal. Here I have my non-metal. I know that metals and nonmetals come together to form ionic compounds. I also know that these opposite charges are going to attract. So I'm going to put them together. You always put the metal first. So strontium, 2 positive. And then you're going to put brackets, selenium, or in this case it's selenide because now it's negative, so it ends in the IDE with its charge. But please don't forget to put the electrons because this is the Lewis structure, so we're counting for valence electrons. And there it is, strontium selenide. That is the ionic compound strontium selenide. So starting from the very beginning, these are just the regular neutral atoms. Those are the Lewis structures. When it loses or gains, they are the Lewis structures for the ions. And when you put them together to form an ionic compound, that's what that looks like in the Lewis structure form. All right, so this was for ionic compounds. Let's try and do one for a covalent compound. Well, I know that covalent compounds are nonmetals and nonmetals, or nonmetals and these semimetals. So I'm going to pick 2 nonmetals. Let's pick phosphorus. So we did phosphorus already. Let's do nitrogen and another nonmetal. Let's do hydrogen. So we can put that together. So you have nitrogen, and nitrogen is in group 5. So if I came back to my periodic table, nitrogen says group 15, but we know it's 3, 4, 5, so it's group 5. And it has 5 valence electrons because it's in group 5. So here's nitrogen. 1, 2, 3, 4, 5. All right. And then hydrogen, I know hydrogen, you guys should know it too. It's in group 1, and so it has 1 valence electron. All right, well, both of these are nonmetals, so technically they both want to gain. So neither one of these is really going to give up. Instead, they're going to share to form a covalent bond. Okay, so 2 nonmetals will come together to form a covalent bond. I'm going to put nonmetal here for both of them so you can make it real clear. All right. I remember in class I told you guys to pair up. So every single time that you had a little single electron like that and a little single electron like this, you can think about them wanting to pair up. So let's go ahead and see. We have nitrogen with 3 unpaired electrons. How many hydrogens do you think it's going to take to satisfy the octet rule for nitrogen? Well, I have 3 unpaired electrons. Each hydrogen has 1, so it makes sense that it would be 3 hydrogens, 1 for each little dot that needs to be paired up. So I'm going to put nitrogen in the middle with its 5. That's just how it exists with 5 valence. That's 6, excuse me. And now I'm going to start adding the hydrogens. So there's hydrogen with his 1. There's another hydrogen with his 1. And another hydrogen with his 1. At this point, hydrogen is happy. We can consider these 2 shared electrons for both hydrogen and nitrogen. So hydrogen has 2 electrons, which is good because hydrogen only can fit 2. He's in group 1. He only has 1 s orbital. So we talked about this when we talked about electron configurations. Hydrogen can only hold 2 electrons. So there's 2 and there's 2. So each one of these hydrogens are happy. What about nitrogen? He wants 8 electrons. Well, we already said that these 2 can count for both hydrogen and nitrogen. So 2, 4, 6, 8. Nitrogen is also happy. So our Lewis structure, without all the smiley faces, those were just me trying to make a point. So that is the Lewis structure right there for NH3. This is NH3. 1 nitrogen and 3 hydrogens. 3 hydrogens. That guy actually has a special name. His name is ammonia, but we'll talk about that later. Also in class, I said that instead of drawing these dots like this, we could have replaced the 2 dots that are being shared with a line. So whether you want to draw them like that or like this, it doesn't make a difference. Just make sure if you draw one of them with the line that they all have the line if they're being shared. So, and then we said that the two lone pairs, the two electrons that are not being shared, they don't get replaced with the line, they just stay as is. All right.